All right, guys, here we go with transformations in rigid motion. We are going to work through a lot of this. I'm going to ask you to pause your video and then probably just show you keys for part of it. I apologize for the poor quality if the quality doesn't come out good for the copy that I uploaded. Mine is awfully blurry. It's supposed to say a transformation is a function that changes position, shape, or size of a figure where we have a pre-image and an image. The input is the pre-image. So, for example, here my pre-image is point A. The image is signified by A prime. Now that's going to be really important that when you do your notations that you use that little apostrophe as a prime notation. Hopefully you have read all of this. If not, if I'm going too quickly, please pause it and read it on your own. A transformation T maps point A to point A prime, or the image of A, and that's how we write it. Now your textbook, the Wiley book, gets into some really specific ways to write out these different transformations. Know that I'm not going to require that of you. I'm going to ask you some basic things that we go over through the worksheets and the practices I expect you to do, but I do not expect you to know the intricate ways to label the different transformations. All right. Coordinate notation is one way to write a rule for transformations. For example, the notation xy maps toward x plus 2, y minus 3 means that my transformation adds 2 to the x coordinate. So it's going to move it 2 units to the right. And it subtracts 3 from the y coordinate, which means it takes that point and it moves it 3 points down. Thus, if I start with a 0.65 and I apply this given transformation, it moves to the right 2 and down 3, so I'm at the point 82. Think about this in terms of an xy coordinate plane. Consider the transformation given by the rule, and then it gives you the rule. What is the domain of this function? What is the range? And describe the transformation. Well, we haven't been given any limitations on our input, so our domain and our range can both be all real numbers. Our domain and our range can both be all real numbers, from negative infinity to positive infinity. What are we doing when we move a point according to this transformation? Well, whatever our starting point was, the next point will be up 1 and to the right 1. 1C, excuse me, my water spilled. 1C maps a point in the coordinate plane by moving it vertically up or down on the x-axis. So if there's a point on the x-axis, it's unchanged by this transformation, but I'm just taking a point and I'm moving it up or down. If I'm moving something up or down onto the x-axis, then that means onto the x-axis. That's my key word. That means that I can use any x value. So my domain is going to be all real numbers. But my point is always going to be on the x-axis. So my range for my functions my points that I get out are all going to have a y value of 0 because they're going to be on the x-axis. What does that transformation look like? Well, I start with any point xy, and I'm not changing the x variable, but I'm changing my y variable to 0 because I'm moving that point to the x-axis. Okay, so let's start classifying and exploring some transformations. If we look at the next page, it tells us that we're going to use coordinate notation to help you find the image. So we're starting with a pre-image. You need to find the image of the right triangle. Plot the images, the vertices, connect the images to draw the triangle. So you're starting with what you're given, and then you're applying the rule, the transformation that you're told to apply. Each of these starts with the same right triangle that is balanced at that origin. And then you apply the given transformation. For this first one, for A, my triangle is going to move to the left 4 and up 3. Now I want you guys to take a second and label your vertices of your original triangle. Now that's going to be true for all of these. I'm starting with A, B, C, where A is that right angle that's sitting on the origin, just to keep it consistent. When I move this triangle, I'm going to the left 4 and up 3. So if I take point A and I move it to the left 4 and up 3, then the image of A is there. Point C moves to the left 4 and up 3 as well, so that's where the image of C falls. Point B moves to the left 4 and up 3, and so that would be B prime. I just realized I didn't get in here with a straight edge of any type. Let me see if I can improvise. To draw a nicer triangle. Now, some of us are pretty decent about being able to imagine where things are going to go. Sometimes, though, we may need to start with a list for our pre-image coordinates and then transform them to the after-image coordinates. For example, transformation B tells me I'm taking the opposite of x. So if x starts positive, the image of x will be a negative value for x. If x were to start negative, the image of x would be a positive value for x. So for xy becoming negative xy, I'm going to go ahead and think about the coordinates for the pre-image of my triangle. Well, my coordinates for my pre-image, A is at 0, 0, B is at 0, 4, and C is at 2, 0. Well, for this transformation, I'm changing the sign, the algebraic sign of the coordinate x coordinate. So 0 is algebraically neutral, so that doesn't change anything, but C becomes a negative 2, 0. So when I do this transformation, A prime and B prime fall right on A and B, but C prime reflects across the y-axis. Look what happens with this transformation. Transformation C, I am switching the coordinates and changing the algebraic sign of y. So I start with xy, I switch them, and I change the sign on what was y. So if I look at, so this was transformation B, now we're going to do transformation C. For transformation C, I'm going to start with 0, 0, well it just stays 0, 0, so A prime stays where it is. B, however, becomes a negative 4, 0, according to the rule of the transformation. So B prime falls at negative 4, 0, there's B prime. And C falls at 0, 2. Notice that I don't change the sign, the algebraic sign on the 2, because it was the x, it's the y that changes algebraic sign. So my triangle for this transformation C looks like that. All right, you guys do D, E, and F. Pause the video, do the transformations for D, E, and F, write down that your list of coordinates if you need to, and then show what happens if that helps you with your graphing. Pause the video, do them, and then come back to me. Notice that I'm being careful to label my image with the correct vertices using the prime notation. That's really important. I'm trying to see what you can see better. I think maybe the purple shows up best. Okay, so there we go. Hopefully yours match mine. If not, take a second and see if you can figure out what you did wrong. And then let's do this reflection down at the bottom. It says a transformation preserves distance if the distance between any 2 points of the pre-image is the same as equal to the distance at the corresponding points of the image. Which of those transformations that we did preserves distance? Well, for A, B, and C, the distance is preserved horizontally and vertically. Now we are going to call this, when we preserve distance, an isometry, which is another name for a rigid transformation. A transformation preserves angle measure if the measure of any angle of the pre-image equals the measure of the corresponding angle of the image. Which of the above transformations preserves angle measure? Well, A, B, and C definitely. Do any of the others? D also preserves angle measure. Now D preserves angle measure, E and F do not. Can you tell why? Hopefully you notice that on D, both the coordinates x and y have been multiplied by a factor of 2, where on E and F, only one of the two coordinates was changed by a factor of multiplication. When we preserve angle measure but not distance, we call that a dilation. A dilation keeps the same shape, but it does not keep the same size. So it's a non-rigid transformation. And then we get to the next page, and we go ahead and our work defines a rigid motion, an isometry, as a transformation that changes position without changing size or shape. On example 3, we're given an image, a pre-image, and an image. I know which one's which because of the notation. And I have to determine whether or not the transformation appears to be a rigid motion. Now, we're not given any measurements. We're not asked to do any measurements. So we're doing it completely by eyeballing these figures, these shapes. On A, though, we are told that the transformation does not change the size or the shape of the figure. And based on that information, we know that it is a rigid transformation or an isometry. On B, I can see that the transformation changes the shape of the figure. This C prime has been pulled out further away from A prime so that that distance is not preserved. Since it changes the shape, it is a non-rigid transformation. And this one is not a dilation. It's not a dilation because it is only this distance that appears to have changed. The distance between A and B, A prime and B prime, appears to be about the same. Okay, on C, it looks like I have the same shape, but it looks like the transformation changed the size. If it changes the size but not the shape, then it is non-rigid and it is a dilation. All right, how could you use tracing paper or transparency to help you identify rigid motion? We've done that one before. You check the size and the shape. If they're the same, then you know you have a rigid motion or an isometry. So, based on that, which of the transformations on the last page appear to be rigid motions? A, B, and C. And we already labeled those as such. Okay, next page, page 38. Rigid motions have some important properties that we have summarized right here. Rigid motions preserve distance, angle measure, betweenness, and collinearity. If one point is between two others in the pre-image, that point is still between those two others in the after image. If 2 points are on a line, then they are still on the same line. That's my collinearity part. All right, this practice page is just applying those transformations as given. We have just done this on the last page. So I want you to complete this on your own. I want you to label it as rigid or non-rigid in the blank below each shape, and pause your video, get that done, and then come back and I will show you the key. All right, so I'm assuming you're back. There's the key for this page. Here's the part where we would have a discussion and answer any questions, and you guys would work together to fix your mistakes. I can't do any of that because it's just me. This kind of teaching is not nearly as much fun. But here you go. Here's the key. Pause this if you need to. I'm going to move on to the next page. Okay, page 39. We have a pre-image, A, B, C, D, and it's after image, A prime, B prime, C prime, D prime, under a transformation. Determine if the transformation is a rigid motion or not. Well, hopefully by looking at these, you have gathered and you have grasped the definition of rigid. Forgive the way the copier copied that over. There's not supposed to be a bump and a break in those sides. These should all be straight sides. That's a technology issue. For the first one, that is not rigid, so non-rigid, because I have a change in shape. Distance has not been preserved along A prime, B prime, D prime, C prime. On 8 appears to be rigid. Looks like the same size and shape if you ignore the bump. 9 appears to be rigid, same size and shape. 10 is non-rigid, and it appears to be a dilation because we have the same shape but a change in size. Now, my dilation doesn't have to mean that it gets bigger. It could get smaller and it be a dilation. Okay, if I have some transformation T that maps a triangle onto its image, the image of segment XY is going to be X prime, Y prime. Where Z is transformed, when I apply the transformation to point Z, I get Z prime. The pre-image, what I started with for angle Y prime, would be angle Y. So all we're doing is finding those corresponding parts. Corresponding parts in the form of segments, points, and angles. Can I conclude that XY is equal to X prime, Y prime? Well, not on what I'm given, because I don't know if my transformation was rigid. If it wasn't rigid, then the length of those segments is not going to be equal. Point M is the midpoint of line segment AB. After a rigid motion, can you conclude that M prime is the midpoint of that segment A prime, B prime? Well, yes, because on my list of properties of rigid motions, of isometries, rigid motions preserve betweenness and collinearity. Preserve betweenness and collinearity. Okay, let's look at the next page. Page 43, we jumped from 39 to 43. Page 43 gives us a table with coordinate notation for reflections in a coordinate plane. Now, I want you to star and mark this table. This is one of the things, this packet's really, really handy for you to have. This is one of the things that I'm going to allow you to include on your reference page for the exam. So make sure you mark that. If you want to reflect a shape across the x-axis, there is your rule for the transformation. If you want to reflect across the y-axis, this is your rule. If you want to reflect across that line, that diagonal line, y equals x, then this is the rule. This reflection, that line y equals x, is this positive line with the slope of positive 1 that goes through the origin. This line is y equals x. When I reflect something across that line, I'm building or I'm showing the inverse function, or the inverse of the function. Okay, draw the reflection in the coordinate plane. You're designing a logo for a bank. The left half is shown. You need to reflect it across the y-axis to complete it. Now you can eyeball it, you can fill in the missing coordinates. You're going to need to fill this in no matter what. If you can't read that, your rule is negative xy. And if I weren't here to tell you that, you would know it from your table that tells you that that's the rule to reflect something across the y-axis, because that's what I'm asking you to do. Anything on the y-axis did not change, it stayed on the y-axis. There are 2 reflection questions down there that you can complete on your own, and then we're going to move to translations. All right, the translations page 53. You see that a reflection is one type of rigid motion, a translation is another. Slides all the points of a figure the same distance, the same direction. This shows us a translation along this vector. Now a vector, that word is vector, V-E-C-T-O-R. A vector is a quantity that has both direction and magnitude, direction and distance. The initial point of the vector is the starting point. The terminal point of the vector is the ending point, so direction matters. And there's 2 different ways to name this vector. I can name it vector EF with that half arrow drawn up above, or vector V with the half arrow drawn up above. That half arrow symbol is the symbol for vector. I could not name this vector FE because that would change the terminal point and the initial point. You always name it from initial to terminal point so that that directionality is given by the name of the vector. All right, another way to name a vector is to use what we call component form. And my component form is tells me how far to the left or right, so a horizontal change first and then the vertical change. And I place that component form in those pointy parentheses is the best way I can describe those, kind of the angled parentheses. So we're going to name the vector and write its component form. We have a vector here, and you can tell by the arrow the directionality so that I can see that M is the initial point and N is the terminal point. So if I want to name that vector using those two points, that is going to be vector MN with my little half arrow above. I didn't mean for that to connect with the N. If I want to write that vector in component form, I need to identify the horizontal and vertical change. Well, I'm moving to the right, so my horizontal change is positive. I'm moving to the right 1, 2, 3, 4 units. And my vertical change is down, so it's going to be a negative vertical change. When I write my component form, horizontal comes first and then vertical. Answering those reflection questions, is vector xy the same as vector yx? No, because direction matters. How are these 2 symbols different? Well, this one names a vector and this one names a line segment. The line segment doesn't have directionality, it just is. It's the piece of the line from here to there. A vector indicates directionality. Okay, let's use vectors to give us a translation. Draw the image of the triangle under a translation along the vector -3, 2. So which way am I moving? Well, I'm moving to the left 3 and I'm moving up 2. If I take this triangle and I move it to the left 3 and up 2, I end up in quadrant 2. And remember, when you name your quadrants, you start at 1 o'clock on the clock and you go counterclockwise to name your quadrants. So go ahead and do that now. It gives us the rule for that translation. It gives you the starting coordinates for the points. Make sure you know how to come up with the ending coordinates for those points. So that you can get the image under that translation naming. Okay. Give an example of a translation that would move the original triangle into quadrant 4. Well, quadrant 4 is down here. So any translation that moves that starting pre-image to the right and down is going to put you in quadrant 4. So anything that moves you to the right and down, the one I gave would have been 4, -4. That's an example. What if I started with my original triangle and I'm translated along that vector and then reflected across the y-axis? What quadrant would your image end up in? Well, that is quadrant 4 as well. All right, now we're back to some practice pages. Well, practice questions. We've got these 3 practice questions. Name the vector, write it in component form. I am going to show you the key here in just a minute. Take a second, pause the video, complete these. There is vector JD, if you had trouble seeing that. There is vector, this one that has S and V. This one has G and H. The arrow is right there. And your answers should match mine. There isn't any leeway for this one. Okay, let's look at page 59. We're going to skip some pages again. Look at page 59. I apologize that is cut off. It says all rotations are counterclockwise unless told otherwise. Assume that when you're rotating in a counterclockwise direction. That's the way we number our quadrants, in a counterclockwise direction. That's the way we rotate things, in a counterclockwise direction. That holds true in trig when you're dealing with graphing. So that's how you need to expect this to happen. Here's another table that provides you rules for rotations this time instead of reflections. Make sure that you star that and watch it. I'm going to give you a couple of minutes because I think you've got the hang of this by now, and then I'm going to put the key up for this page. So pause the video, complete this page, and then look for the key. All right, guys. I feel like the baking show person who pulls the completed cake out of the oven. Here's the key. Check and see how you did. And then the last page is also going to be practice. So we're going to turn over there and talk about it just for a second, and then I will give you the key for that. Okay, when we look at this final page, some of these are a little difficult to see. So I'm going to go ahead and trace out so that you can see. I think you can see all the others fine. I think number 7 was maybe the only one that was a little tricky. It tells you the rotation. So you're going to, this is the pre-image, you're going to sketch the image, draw the image of the figure under a rotation of 180 degrees. This one is 90, then I do 270, 180, and answer these questions below. I encourage you to go to the side and set up a chart where you list the coordinates as they stand and then give what happens to those coordinates after the rotation. Once again, I'm just going to pop the key up there, so pause the video. And we're back. There's the key for 1 through 9. And then I'm also going to show you the key for the bottom for number 10. And I encourage you to contact each other or to contact me if you have questions about this activity.